Hello and welcome. So in this lesson, I'm going to go over quantum numbers. Now, there is going to be quite a bit of information, so please feel free to pause, rewind, to try to reabsorb what you heard, and of course, try practicing. Practice as much as you can. We'll get together as a class, virtually, of course, and we can practice going over some examples. Okay, let's get started. So we've led up to this by looking at how the model of the atom has developed. One of the first scientists that we talked about that started this path into the quantum model is Bohr and his study of the spectrum of the hydrogen atom, of an excited hydrogen atom. And we talked about this for a while now, and we're referring to different scientists. But notice that the principal quantum number, the first quantum number, showed whole number properties in different measurements of energy. So the first quantum number n relates directly to the periodic table in that it is a few things. So it indicates the amount of energy that an electron has at a certain level, its distance from the nucleus, and of course its a size of the electron cloud. We also get into the number of electrons, but I'm going to go back to this in just a bit, but I want to see if I can get you to a periodic table. We'll go back to this. All right, so n is essentially, n essentially refers to the rows in the periodic table. So row 1, row 2, 3, 4, and so on. So n is equal to all of those values, right? So that's your first quantum number. I'll go back to that periodic table. Okay, so they're whole number values that relate directly to the row in the periodic table. So n is equal to, essentially just means, and refers to the energy level or the row in the periodic table. Okay. Also mentioned that the distance from the center of the atom to wherever that electron is grows as that n number increases. So the first energy level being 1, electrons are at this relative distance from the nucleus. So you can think of your nucleus as being at this very end here. The further electrons are away from it, the more energy they must have to maintain that orbit. So n is equal to 1 is around here, relatively speaking. Now, when you did energy level diagrams in grade 11, it may have seemed evenly spaced out, but in reality, the distance between the first energy level and the second path, the second energy level, n is equal to 2, is quite relatively different from others. You can see that there's quite a distance between n is equal to 1 and n is equal to 2. Right? But then we progress, n is 2, n is 3, and 4, and they tend to get closer and closer together. You may also see, and I'm not going to ask you to know this, but you may also see that the principal quantum number n sometimes is referred to by letter as well, where the first number for the first, or n is equal to 1 is k, when n is 2 it's l, when n is 3 it's m. Now, if you do some research online, or maybe you find some worksheets or some practice and refers to principal quantum letters or numbers k, l, m, n, it does refer to a specific number. I'm not going to make reference to this at all. You won't need to know that, but just so you know, that is out there. So another point previously was that the number of electrons is determined by the principal quantum number. So if n is equal to 1, we know that belongs to hydrogen and helium. N is equal to 2, well, now we're in the second row, and that involves 8 electrons, or 8 elements. Right? We'll get to more of that as we look at the periodic table some more. So what Bohr did, as we saw previously, Bohr found that there were 4 lines in his hydrogen line spectrum. But with the improvement of observation techniques, it was discovered that there were actually more than 4 lines. Right, so look at all these lines here. So Bohr was missing something. We already talked about how Bohr's predictions worked really well for hydrogen, but not so much for larger atoms. There was the initial components, the initial parts of his theory were sound, and actually still are. But as you progress to other atoms, they essentially found that there were missing parts. We didn't know the entire story. And that was proof. So to add to the theory, to build on the atomic theory, then a German physicist, Arnold Sommerfeld, said that there must be something else to describe what's happening, to describe the resolution, the better resolution we see here, where there are certainly levels, but there must be sub-levels or subshells. So within these energy levels, there are subshells. That brings us to our secondary quantum number, quantum number and referring then to L. So we have our first quantum number is n, second one is symbolized by the cursive letter L. Okay, and that describes the shape essentially of the orbital. There are spherical shapes and dumbbell shapes, double dumbbell shapes when you get to other levels. This one's another one called donut. Another one's called fancy. Don't have to worry much about those. We're actually going to focus on these. So spherical. Sorry, I'm getting used to this pen here. Spherical and dumbbell are the ones that we will focus on the most. Okay, so the number of sub-levels or number of shapes within an energy level n, right, that is directly related to the n value itself. So when n is equal to 2, we have 2 different shapes. When n is equal to 3, we have 3 different shapes, S, P, and D. Let's see if I can find a periodic table. Here we are. Okay, so let's change color here. This will do. Okay, so here is our, from back to grade 11, this is our S block. That gives you a spherical shape, right? This is our, not including hydrogen, sorry, helium, not including helium. This is our P block, right? So this is S over here, this is P over here, right? Then along here, oops, that should have been straight. Here we have our D block, and at the bottom, we have our F block. All of these, so this S, P, D, F, they refer to the sublevel. They have different shapes. Again, we're focusing on S and P. We will certainly talk about D and F, but we're focusing on S and P. Okay, so if n is equal to 2, that means if n is equal to 2, right here, we have an S shape and we have a P shape. If n is equal to 1, right here, we have just an S shape. Remember, helium is actually part of S, so we just have one shape here. Now, if we have n is equal to 3, we have S, P, and then if you recall from grade 11, the third energy level actually continues in the fourth row right here where D is. We'll practice more of that. Okay, so that's your secondary quantum number referring to the suborbitals. Right, suborbitals, so secondary quantum number, of course, symbolized by the cursive L. Maybe I'll go back to my other colored pen. Okay, that actually has numbers, just like n has numbers 1, 2, 3, 4, and so on. L has numbers 0, 1, 2, and 3. 0 stands for the S shape, 1 stands for the P shape, 2 for D, and 3 is for F. Notice their shape, their names. You would think that S is for spherical, but it's not. This is the actual names. Why these are the names, don't quite know, but just know that S is your spherical shape. Think of it as a beach ball, where the electrons are all on the outside of that beach ball, none on the inside, only on the surface, not in the center. P is your dumbbell shape. We'll talk more about that and draw some pictures. D has strange shapes. F, many scientists don't actually know exactly what those shapes are. They're still discovering them and studying that part of the periodic table. Okay, so values. If n is a certain value, your range for L is going to be from 0 to n minus 1. Let's practice that. So this example is asking us to state the secondary quantum numbers for n is equal to 2. So if n is equal to 2, and if the range is from 0 to n minus 1, that means if n is equal to 2, the range is going to be from 0. The possible range of shapes are going to be from 0 to 2 minus 1, which is really 0 to 2 minus 1 is 1. So your range is going to be from 0 to 1, which means that it'll just be, your possible numbers are 0 and 1. 0 stands for S, 1 stands for P, right? 0 stands for S, 1 stands for P. So the possible shapes are S and P with these numbers 0 and 1. Right? Pause if you need to. We're going to get to more examples, and you work on practice this yourself, and we'll go over it as a class. Okay, again, just to review, this is your S block here, your P block, your D block, and your F block. Okay, some examples. So what are the allowed values for L, that's your secondary quantum number, if n is equal to 3? So remember, well, here are the answers, but let's just focus on the left here. If the range for L is 0 to n minus 1, that means that it has to range from 0 to 3 minus 1, because our principal quantum number is 3, which means 3 minus 1 is 2. So our range is going to be from 0 to 2. That means it has to be in whole number integers, 0, 1, and 2. In other words, S, P, and D. So any element that has n is equal to 3 could possibly have, in other words, could possibly have these 3 shapes within it, an S, a P, and a D. Spherical, dumbbell, and your funny shaped Ds, which we'll show you pictures of in a bit. Okay, your third quantum number, or your magnetic quantum number. This just refers to the orientation. Now, if you take a beach ball, right, take a sphere, take a beach ball, and you spin it, you rotate it, that ball isn't going to change the way it looks. Now, assuming it's not the really nice flashy colored beach balls, it's just a simple white, plain, uniform color. If you rotate this in any direction, it's not going to change its orientation. It's not going to change its shape in any way. It just has one orientation. Now, if you take a dumbbell shape, like your p orbitals, now you can rotate this in different directions and it will actually look different, whereas the beach ball didn't, this will. Okay, so that's essentially what this quantum number is referring to, the orientation of these different shapes. It doesn't matter for S, it does for P. And I'll tell you why in a bit. Right, before I move on, the range for these numbers is, so the symbol for this number is ML, cursive L. Okay, and that ranges from a negative L value to a positive L value, and all positive and negative integers between. So before I get into the numbers, we certainly will get into identifying the numbers. I do want to talk about orientation a bit. Now, this is where my pen skills on this sketch pad is going to really be tested. So I might have to erase, might have to try this over again, but we'll give it a try. We know that since grade 9, you've learned about the Cartesian plane, or even since grade 10 probably, scatter plots. You know that the Cartesian plane has an x and y axis. Now we know that space actually has 3 spatial dimensions, and I'll draw them out for you, at least try. Okay, that's not too bad. It could be better, but I'll go with that. Right, so in grade 9 you learned that this is your x and this is your y axis. Right, x and y. Okay, but there is actually, I hope I get this one. That'll have to do. Okay, it's actually third axis. Now there's different ways to write x, y, z here. I was taught and I've seen a lot of this, so I'm gonna keep with this. So z, this remains as x, and this will be y. Heard someone once describe this as your Cartesian plane flattened to the ground, and you add another axis in the vertical direction. So this is your 3-dimensional, three axes in 3D space. All right, so different color pen. Let's go with red. In your p orbital, so this is just going to look at p for now. In your p orbital, you will have a p orbital that exists. Now these should all intersect here, but forgive my drawing skills. Your p orbital, your px, you will have an orientation of a dumbbell shape that looks roughly, very roughly, like that. Okay, imagine it's drawn a lot better. That's how it'll look. All right, then let's go with green. Then in your y-axis, you'll have a similar shape, but in a different orientation. Let's see, oh, I'm getting better at this perhaps. Okay, so that is your py in the y orientation. Then let's use a different color. Let's try blue. Then in your pz orientation, you have another dumbbell shape. Right? So that way you have these three different orientations, x, y, and z. That quantum number referring to the orientation identifies what orientation this p orbital will exist in. Specifically, p does also, your s orbitals do have does have an orientation, which we'll talk about in just a minute. Well, it just has one, but we'll get to that. Switch back to my select tool. Okay, here it is. So your s orbital, your 1s is a closer to the nucleus, and it doesn't have any other different orientation. You can rotate this and it won't change its orientation. And we continue. This is 2s, and it just grows. 3s, it just grows. Doesn't have any orientation, any different orientations. Whereas your p orbitals, they do. They can be x, y, and z, right? All the same shape, all that dumbbell, that typical dumbbell shape, but in different orientations. Now the notation. This is the coefficient here. The number itself refers to your n value, your principal quantum number. Your secondary quantum number, you're referring to your subshells or your orbitals, your shapes, that in this case is p, and x refers to the orientation. Okay, now we'll look more at this when we look at our next lesson, but for now let's go over the quantum numbers and what they mean. Here are those d orbitals, the 5 d orbitals. You will not need to draw these. I thought you should see them because I would have wanted to see them, and here they are. You won't need to draw them. There's your donut. there are your double dumbbells. Let's move on. Now here are the quantum numbers. If you understand this for this lesson, then you've done extremely well. And it may take several times, several views. You may have to pause throughout. Please feel free to do that. So when n is equal to 1, let's get a pen, yellow. Okay, when n is equal to 1, you then have a range for L, which is 0, right? Remember that? Or maybe yellow wasn't a great idea. Let's change that. Okay, so your range for here is 0 to n minus 1. So 0 minus, well, that would give you a negative number. So only one orientation, 0 to 1 minus 1, wasn't thinking straight. 0 to 1 minus 1 is just 0 to 0, which just gives you a secondary quantum number of 0, which refers to the S shape. It only has 1. Then for your ML number, now your ML number refers to negative L to positive L. Okay, going back to your L values, if it's 0, it's negative 0 to positive 0, which really just means 0, just one orientation. Now that makes sense because that beach ball, no matter how you turn it around, it's going to look the same. It therefore only has one ML number. Okay. And number in this subshell, well, there are just two. There's number of elements, there's just hydrogen and helium. Okay. Number in total, and that n is equal to 1 row is just hydrogen and helium. Moving on. N is equal to 2. Here you also have 0, right? Because if you go back, you do have a couple of elements. I wonder if I have a periodic table here. Should have placed one. I do. Okay, so we're now in 2. N is equal to 2. S, we do have 2 elements here, right? We also have boron through neon here in our p orbital for a total of 8. Okay, but first, our S shape. Our S shape has just the one shape, which is S is 0, and the range for 0 is -0 to +0, only one orientation, which is just 0 for Ml, and we have 2, and that is lithium and beryllium. 2. Next, the other possible secondary quantum number within this range for n is equal to 2 is 1, referring to the p orbital. Going to your p orbital, we have 1, 2, 3, 4, 5, 6. Right, 6 elements. They have different orientations: -1, 0, +1. Okay. Now this refers to the -1 refers to x. This is y. 0 is y. Z is +1. We will get into more detail in our next lesson, but these are the different orientations. -1 is x. 0 is y. +1 is Z. Okay. Briefly, I'm not going to get into 4, but if they follow the same pattern, if our n value is 3, we have 0. We already talked about 0. We have 1. We saw the orientations for -1 or x, 0 for y, +1 for z. For 2, referring to your d orbital, here we have 1, 2, 3, 4, 5 different orientations. Those are those 5 funny-looking D shapes, right? Okay, so I want to go back for just a bit to my funny-looking drawing here. Okay, I think I'll keep this color. No, I'm going to change to black. So I didn't talk about electrons. Every suborbital, so second quantum number, every suborbital represented by L has 2 electrons. So along the x-axis we have 1 and we have 2. Along the y we have 1 and we have 2. On the z we have 1 and we have 2. For a total of 6 electrons for all our p orbitals. That should make sense because going to our periodic table, we have 1, 2, 3, 4, 5, 6. Hopefully this is starting to come together. Our s orbital, I didn't draw the s orbital. This is where it's going to look a bit funny, but our s orbital would look roughly, very roughly, like that, right? Sphere, circle. One, for it not to look too messy, I'm going to put these electrons here. That is made up of 2 electrons. Each suborbital has 2 electrons. Those are, and if we're drawing 2s and 2p's in that picture, those are the electrons for lithium and beryllium. Finally, after the Bohr-Rutherford model, after about 4 years of that, you now know that this is really how, well, closer to the real model of the atom. Okay, a couple of examples and we are almost finished. Again, feel free to pause. I'll do one. This one will take just a minute or two. The next one will be a bit shorter because we're going through essentially the same electrons. Okay, so nitrogen. Let's get to it. Nitrogen, atomic number 7. Back to our periodic table. Nitrogen is right here. Star that. Nitrogen's right there. It has 7 electrons. First electron, first energy level, S shape, 0 orientation. We haven't talked about spin yet, but hold off on that. We're going to concentrate on these 3 for now. We will get to that 4th quantum number in just a bit. Okay. Then the next electron. We did hydrogen. The next electron is helium. Still in the first quantum number, in the first energy level, S shape, 0 orientation. But now looking at this number, and we'll talk about what that means exactly in just a bit. But the 4th quantum number for our first electron is, we'll call it our spin. It's +½ and the next one is going to be -½ Okay, now that just refers to how electrons spin. They can spin in a clockwise direction, or they can spin in a counterclockwise direction. That's given either a positive value or a negative value. +½ or -½ Moving on. Now we're into our second energy level. Right, still within the s orbital, still has a 0 orientation. We have +½ to begin, just like we started off here. You always start with +½ right? And that describes a 3rd electron. That would be lithium. Beryllium is next, still within that s orbital, second energy level, s orbital, 0 orientation, but we can't be positive half, we have to be negative half. Right? One electron has to spin in a clockwise, another one in a counterclockwise direction. Right? Going back to your physics class, we know that movement of electrons dictates the direction of the electromagnetic field. Right? So if they're in the same magnetic field, they would repel more. So they need to be in different ones, opposing ones. So we represent that those opposing spins by these numbers, positive half and negative half. All right, still in our second principal quantum number, but this time, look, we are no longer at S, we're now at P. Okay, so first orientation. We know that P ranges from -1 to +1, so -1, 0, and +1. -1 is X that has a positive half spin, 2px. Next electron, still in that P shape, that P section, P block of the periodic table, is this orientation represented by 0, so that's going to be Y in the Y orientation. And that spins, it's in a different orientation, so it doesn't have to switch to negative. It's going to maintain that pattern of +half. This is now 2py, all spinning in a clockwise here, clockwise here. Right? And finally, our last electron, still in the p orbital. It has a z orientation though, right? -1, 0, and 1. These are our possible ML numbers, orientation numbers. You have positive half, positive half, positive half. Okay, now the difference in our next example, it isn't a whole new example. Really, it's just one element ahead, right? We did nitrogen. Now we're going to do oxygen. Okay, look, I'm not hiding anything here. Everything in this table is exactly the same. The only thing that's different is when we get to this point. Sorry, when we get to this point. Here we have our second principal quantum number is 2. Our L value is now begins at P. So here we have X half 2px, right? The one electron, now we may have thought, well, maybe we're going to continue adding electrons to the very bottom here, but we're not. This electron is now going to begin to fill the X orientation, the 2px orientation. Look in the -1, meaning X, except its first electron you saw from nitrogen is +half. The next electron is -half. The rest of the electrons stay the same. Going back to our periodic table, we have 2s, 2p. It goes like this: X, Y, Z. All of these are in a positive half spin. Then once these orientations are half filled, then they repeat. These electrons repeat. They go X, Y, Z. Except those ones are now in a negative half spin. Only when they're half filled, when these orientations are complete, are half complete, then can they pair up. So oxygen being in the same orientation as the electron for boron is only different by its spin, by the spin of that electron. And this is a bit more about that. So clockwise, counterclockwise, represented by half, negative half, and positive half. This summarizes everything. I mean, if you can go over this yourself, you got it. We won't go into a lot of the lower periodic table, but that will summarize all of it for you. You can refer to that, right? Just this summarizes it, I think, a lot more concisely. So S is this block, D is this block, P is that block, F is that block, right? This is our second, third, fourth, fifth, and so on. Principal quantum numbers, secondary quantum numbers referring to those different shapes. Your orientation, your third quantum number is, for S's case, is just 0, it only has 1. But for P, we have -1, 0, +1. Then we repeat that. Only after they're, you begin to fill them up. So -1, 0, +1. X, Y, Z, X, Y, Z. These are half spin. These are rather positive half spin. These are negative half spin. Works the same way for D, except this time we have 10 electrons. right? Every suborbital has 2 electrons. So for the -2, we have 2 electrons. There's 2 -2s, one here, one there. For the -1s, we also have 2, one here, one there. And it's always just double. So we have 5 electrons here, 5 electrons here. They are all in these 5 different orientations, paired up in those 5 different orientations for a total of 10 electrons. Half of them will spin in one direction and the other half will spin in the other direction. Okay, just to throw one more thing there, because we already haven't done enough, right? Pauli's exclusion principle essentially just says that no 2 electrons in a given atom can at the same time have the same 4 quantum numbers. Okay, now there's a lot of research going on here with absolute zero experimentations where suddenly this rule may not exist, but that's beyond the scope of this course and most courses you'll likely take. But the Pauli exclusion principle essentially just says you can't have 2 electrons with the same set of 4 quantum numbers inside a given atom, right? Here is your homework. Textbook is great with this. We will practice this. We'll meet together as a class and talk about these examples. I have extra practice as well posted on our class website. Right. So that's it for now. I hope this wasn't too confusing. It is a confusing topic, so we will meet again and go over it as a class virtually.